Hello everyone. This lecture is a direct continuation of the previous lecture in this module and provides an example of a TAPS implementation called NEAT. So what is NEAT? Well, the NEAT system offers an enhanced API for applications to access transport services. It also includes mechanisms for protocol selection and fallback in case network paths do not support certain transport services, opens up for the introduction of new transport services, and opens up for the introduction of protocol mechanisms that take care of middle box traversal. Or, in sum, NEAT is a transport system designed to offer a flexible and evolvable transport service in a protocol-agnostic way in current TCP/IP networks. A second question you might ask is, what are the benefits of using NEAT as compared with, for example, the traditional sockets API? Well, there are several advantages, the most important ones being listed on this slide. First, the NEAT system is evolvable. It enables the addition and support of new transport services as they emerge, a key requirement for NEAT to sustain over time. Second, the NEAT system offers a protocol-agnostic and generic API that effectively decouples the API from the underlying transport protocols and their specific transport services. In that way, applications may be developed once and still take advantage of new transport services as they become available. Third, the NEAT system is directly deployable in existing TCP/IP networks. It is not dependent on any particular network technologies or protocols. This is of course a key property considering the ossification of the Internet discussed in previous lectures. Fourth, the NEAT system is platform independent. It does not rely on any particular operating system or physical architecture. So for example, NEAT already runs on several platforms including Linux, Mac OS and FreeBSD. And last but not least, the NEAT system aims to comply with the current standardization efforts in the IETF TAPS working group and their goal to bring forth a common, flexible and evolvable transport services architecture. In fact, NEAT has in many ways served as a platform for experimentation and acquisition of experience around TAPS. This slide provides an overview of the NEAT system. Applications access the NEAT system via the NEAT User API and its associated interfaces. The NEAT User API offers transport services similar to those offered by the Socket API, but using an event-driven style of interaction. More on that later in this lecture. The core components of the NEAT system are categorized into 5 groups: framework, selection, policy, transport, and signaling. The framework components provide the functionality required to use NEAT, for example, the management of flow endpoints, the API framework, the logic behind the framework, and the domain name resolution. The selection components are responsible for selecting an appropriate transport endpoint and set of mechanism for path support discovery using so-called happy eyeballs mechanism. More on happy eyeballs later. The policy components enable the application and management of different transport policies and include a policy manager, a policy information base, and a characteristics information base. For each new connection requested by a NEAT-enabled application, the policy manager is responsible for generating a list of candidate transport solutions which meet the requirements defined by the application. To this end, the policy manager takes into account all known information about the network stored in the characteristics information base, as well as any applicable policies defined in the policy information base. We will talk more about the policy components in a bit. The transport components offer applications seamless access to get features of standardized transport protocols while ensuring that packets get through the network in the presence of non-supported middle boxes or challenging network paths, and providing a path to seamlessly introduce new transport protocols or transport protocol features. The transport components offers a consistent abstraction over underlying transport protocols and allow applications to use transport protocols implemented in the operating system kernel as well as those running in the user space. Finally, The signaling components provide advisory signaling to complement transport components, for example signaling between end host and middle boxes, and support for handover between networks and/or network technologies. A neat flow is set up as depicted in this slide. It all starts with the application specifying properties of the communication, and the application calls the function neat open in the neat user API. More on the neat user API in later parts of this lecture. Second, the neat framework sends application properties and inferred properties to the neat policy manager based on the destination domain name. In the third step, the policy manager finds available transport candidates on the basis of the available policies in the policy information base and cached information in the characteristics information base. Next, in steps 4 through 9, the neat framework takes the initial step of transport candidates returned from the policy manager and on the basis of this set builds a list of transport candidates to be tried out by the so-called happy eyeballs component, one of the more important components of the neat framework. Also in step 9, the happy eyeballs component goes through the list and makes connection attempts. How this is done will be discussed in a moment. However, it ends with one connection being the selected one. In step 10, the neat framework starts polling the socket internally and reports back to the application that the connection has been established. The flow opening procedure ends in step 11 with the neat framework asking the policy manager to cache the results of all connection attempts carried out by the happy eyeballs component in step 9 in the characteristics information base. In that way, neat avoids carrying out unnecessary connection attempts in the future. The neat policy components enables the specification of policies which, together with knowledge about the system on which neat runs and network characteristics, determine the transport protocol to use for a particular neat flow and its configuration. The neat policy components include the policy manager, the policy information base, and the characteristics information base. For each new connection requested by a neat-enabled application, the policy manager is responsible for generating a list of candidate transport solutions which meet the requirements defined by the application. And to do this, the policy manager takes into account all known information about the network stored in the characteristics information base, as well as any applicable policies defined in the policy information base. The characteristics information base acts as a repository storing information about available interfaces, supported protocols, network properties, and current and previous connections between endpoints. The policy information base acts as a repository that contains a collection of policies, where each policy consists of a set of rules linking a set of matching requirements to a set of preferred or mandatory transport characteristics. Policies can be added by a system administrator, external entities, or applications and have different priorities. In addition to policies, the policy information base also contains so-called profiles, which are policies that are applied before the lookup in the characteristics information base. Profiles are typically used to translate high-level properties into sets of concrete, low-level properties. It should also be noted that besides when they are executed, policies and profiles are functionally identical. The happy eyeballs component is one of neat's selection components. The figure on the right-hand side of this slide shows what happens in this component when a client and a server, both of which support TCP and SCTP, with SCTP the preferred protocol, try to establish a connection. Recall that a list of transport candidates serve as input to happy eyeballs. Each transport candidate on the list has a priority, which is a positive integer, with 0 being the highest priority. The list is sorted in ascending order on the basis of the priority. The happy eyeballs component goes through this list and concurrently tries out each of the candidate transport solutions in the list and finally returns a handle to the first successfully established connection. The priority of a transport candidate translates to a delay between the candidate in question and the previous candidate. So the connection attempt of a low priority transport candidate is delayed with respect to a high priority candidate. In this example, the TCP connection attempt is delayed with respect to the SCTP connection attempt. Since happy eyeballs should not waste network resources by routinely making simultaneous connection attempts, the happy eyeballs component instructs the policy manager to cache the outcome of previous connection attempts. In our example, we see that although the TCP connection attempt loses, the fact that it was successful is anyway cached. The NEAT system provides a callback-based API to developers of networked applications, an API that builds upon libuv, the asynchronous IO library that underlies the JavaScript server engine Node.js. The most important concept in the NEAT API is that of a flow. A flow is similar to a socket in the traditional Berkeley socket API. It is a bidirectional link used to communicate between two applications. In the same way as with a socket, a flow uses some transport layer protocol to carry out the communication between the applications. However, one important difference is that a flow is not as strictly tied to the underlying transport protocol as is a socket. In fact, a flow may be created without even specifying which transport protocol to use. This is not possible with a socket. A context is a common environment for multiple flows. Along with flows, it contains several services that are used by the flows internally in NEAT, such as a DNS resolver and a Happy Eyeballs implementation. A flow may only belong to the context in which it is created, and it cannot be transferred to a different context. Finally, properties constitute the way in which applications specify the transport service they desire. Different types of applications have different requirements. For example, a video conference application might specify properties such as low latency and high bandwidth, while a transfer application may specify properties such as high reliability and high bandwidth. The program excerpt on the slide shows the salient features of a simple client application. First, we have the callbacks. The three most important callbacks in the NEAT API are onConnected, onWritable, and onReadable, of which only onConnected is shown in the excerpt. The onConnected callback will be executed once the flow has connected to a remote endpoint or a flow has connected to a server listening for incoming connections. The onWritable and onReadable callbacks, which are not shown, are executed once data may be written to or read from the flow without blocking. The NEAT flow operations struct in onConnected and in main is used to tell NEAT what to do when certain events occur, for example once it is possible to read or write a flow. The actual assignment is done via the function NEAT set operations. The flow establishment is done by the function NEAT open, which engages the policy manager and Happy Eyeballs to accomplish this. Since NEAT is a callback-based API, an event loop needs to be started, and this is done with the call of the function NEAT start event loop. To sum up this lecture, NEAT is a flexible and evolvable transport system that is readily deployable in current TCP/IP networks, and which aims to adhere to the standardization of transport services architecture going on in the IETF TAPS working group. The NEAT system offers a protocol-agnostic, callback-based API to application developers that effectively decouples applications from the underlying transport protocols. And this concludes my lecture on NEAT. Bye.